Okay, hello everyone. My name is Bobby Mahmood and I'm a PhD student at McGill University under the supervision of Professor Lino. Today I will present our paper, which is accepted for publication in ICC 21. The paper is titled as Massive-MIMO Hybrid Precoder Design using Few-Bit DACs for 2D antenna array structures. This is the brief outline of my presentation. So I'll start from the introduction, followed by the research motivation. Then I'll discuss the system and channel model. Then I'll present the hybrid precoder design using the low resolution DACs, followed by some results and the conclusion. So massive MIMO, we know that is the arrangement of the large number of the antenna elements at the base station. And by this arrangement, we can have many advantages. For example, we can have the high beamforming gain, a large number of the users, they can be supported, and we can also have the high summary due to spatial multiplexing. But the question is that do these gains, they increases linearly by increasing the number of the antennas? So there is a potential limitation which is offered by the interference. So the interference, it could be the multi-user interference, which could be experienced by the users within the same cell. And also the user can experience the interference from the users from other cells, which is referred as the inter-cell interference. So in order to better manage the interference, if we have the perfect channel knowledge or the perfect channel state information, we can manage the interference. But in the conditions where we do not have the perfect channel knowledge, we can encode the signal at the transmitter, which is usually referred as the precoding. So in precoding, we have the full digital precoding where we are using only a single stage precoder, which is used to reduce the multi-user interferences. And the number of the RF chains in this case is equal to the number of the antennas. So if we consider the massive MIMO, these number of antennas, anti could be in hundreds, which means that the RF chains, they can also be in hundreds. So the fully digital precoding can provide good performance, but at the expense of the cost and the complexity. The other hybrid precoding design is the other precoding design is the hybrid precoding, which is a two-stage precoder design where the RF precoder is used to reduce the number of RF chains, and the baseband precoder is used to reduce the multi-user interference. And the RF chains here, which are connecting the baseband and the RF precoder, they are upper bounded by the number of the antennas, and they are lower bounded by the number of the data streams which we want to transmit. So we can see that the hybrid precoding, it can offer the performance close to the fully digital precoding with much reduced complexity. So the research motivation for this work is, first of all, we need a large number of we need a large number of the antennas at the base station, because by increasing the number of the antennas at the base station, we can actually support large number of the users. But it has been seen that if we arrange the antenna elements in one dimensional, which is a uniform linear array, it may not be possible to physically arrange them. Also, one-dimensional array structure, they may not be able to simultaneously eliminate both the azimuth and the elevation angles. So which means that when we talk about the 3D beamforming, we would like to consider the 2D array structures. So there are different array structures which we are considering in our work. So we are using uniform linear array where the elements are in the form of a line separated by equal spacing. And then we have the uniform circular array where the elements are arranged in the form of a ring. Again, they have the equal spacing D. In uniform rectangular array, the antenna elements, they are arranged in the form of the plane in two-dimensional. And then we have the concentric circular array where we have multiple rings, and the antenna elements, they are placed in these multiple rings, which offer us a much higher spatial efficiency. Another research motivation for this work is that why we need the low resolution hardware components. So we saw that the fully digital precoding, it can provide good performance, but it requires large number of the RF chains, and it is impractical in massive MIMO because of the cost and the power consumption issues. The hybrid precoder can give the performance close to the fully digital precoding, but again, it requires the use of the full resolution hardware components, which are still costly in massive MIMO. So the idea is like, can we approach the performance of the fully digital precoding by using the low resolution hardware components? And in this particular work, we are considering the low resolution digital to analog converters. Now I will present some of the previous work which has been done using different array structures. So for uniform linear array, there are some papers which design the hybrid precoder using uniform linear array. For example, the paper by Sorabi, he designed the hybrid precoder and reduced the number of RF chains. He also showed that the use of low resolution DACs can actually achieve the performance of the infinite resolution DACs. Similarly, for the uniform rectangular array, the paper by Astil, where he designed the hybrid precoder using users' angular information, it shows that the URA is also capable of providing higher sum rates close to the fully digital precoding. For the circular arrays, we have the uniform circular array and concentric circular array. And based on the correlation of the channel vectors, it is possible to provide sum rates close to the fully digital precoding by using the circular array structures as well. So the system model, in the system model, we have the RF precoder BA and the baseband precoder BD. They are connected by the number of RF chains, and as I discussed before, the number of RF chains, they can be greater than the number of the data streams, which in this case, they are equal to the number of users K, and they are upper bounded by the number of the antennas. To consider the low resolution DACs, we are considering the qubit DACs in the RF chains. Also, we are modeling the quantization noise using the additive quantization noise model. So the table 1 gives us the distortion factor used for different bits of the DACs, and also the quantization noise is modeled using this equation. For the channel model, we are considering the one ring model, where we have the user, which is surrounded by the ring of scatterers. So the ring radius is given by R, and the signal which is transmitted by the base station antennas at the azimuth angle phi. So based on this user's angular information, we can actually calculate the correlation between the channel coefficients. So for example, here we have equation 1. It calculates the correlation for the ULA for the one-dimensional antenna array, and then equation 2, it can be used to calculate the correlation between the channel coefficients of the antennas for the 2D array structures, which in this case is URA, UC, and CC. So after finding the correlation, we can actually formulate our channel vector based on the kernel wave decomposition. So based on the eigenvalues and their corresponding eigenvectors, we can actually calculate the channel vector for the user K. Now I will present the hybrid precoding design using the low resolution DACs. So first of all, we have the total K users, which are divided into G groups, and each group we have KG users, so we are using equal distribution. So we calculate the channel vector for one user, and then based on that, using the kernel log decomposition, we can formulate the channel metrics for one group. G subscript represents the group G. Then we can concatenate the channel matrices for all the groups to have the complete channel matrix. So the aim is to maximize the signal to quantization, interference, and noise ratio. So here in equation 4, we can see that we want to maximize the numerator while reducing the multi-user interference and the quantization noise. And the way we can do is by properly designing the RF and the baseband precoders. So the RF precoder BA is designed based on the dominant eigenvalues. This superscript plus, it represents the eigenvectors corresponding to the dominant eigenvalues. So we can formulate our RF precoder for one group, and then based on following the similar procedure for all the groups, we can have our complete RF precoder. The overall reduced dimensional effective channel matrix is then given by equation 5. So here we can see that the diagonal entities, they are the effective channel matrix for the group G, whereas the off-diagonal entities, these are actually the multi-user interferences, and the aim is to minimize or to reduce them. So we can design the baseband precoder BD to actually reduce the multi-user interference. We are using the regularized zero forcing, which is based on the channel inversion. So here we have alpha, which is the regularization parameter, and eta is the normalization factor, which is used to satisfy the power constraint. Now I will present the illustrative results for the designed hybrid precoder using the low resolution DACs. So we are using 100 antenna elements, and we are considering 3 groups, user groups, which are located at 30, 90, and 150 degree. And in each group, we are considering 3 users. So we can see that the black line here is the fully digital precoding sum rate, and we can see that it provides the highest sum rate for all the array structures for ULA, UCA, URA, and CCA. And this is because the fully digital precoding requires the use of 100 out of chains. Then we have the star shaped curve. This one is for the hybrid precoding using the full resolution component. So we can see that it provides the performance close to the fully digital precoding. And it requires only the use of 9 out of chains. So we can get the performance close to the fully digital precoding in URA and CCA by using only 9 out of chains. Then we consider the analysis for the different bits of the DACs. So we can see that 1-bit DAC provides the lowest sum rate. However, in CCA, it can provide the sum rate higher than the other array structures. Also, if we increase the number of the bits, so we can see that the 4-bit DACs, for example, it can provide the sum rate close to the infinite bit DACs in the case of the CCA and URA. Next, we compare the energy efficiency. So the energy efficiency is plotted versus the different number of the bits of the DACs. So Q is the number of the bits of the DACs. So we can see that by increasing the number of the bits of the DACs, the energy efficiency overall decreases because the power consumption, it increases by increasing the number of the bits. So we are providing for 2 different scenarios. Figure A is for the very low SNR, minus 20 dB, and figure B is for high SNR, when we are using 20 dB. So we can see that fully digital precoding here, it is used for the UCA because UCA provides the highest fully digital precoding sum rate. We can see that though FDP can provide high sum rate, but it is not capable of providing the higher energy efficiency because it requires the use of 100 out of chains, which are energy expensive. Also, we can see that maybe 1-bit DAC is able to provide high energy efficiency at very low SNR, but if we increase the SNR, we may need 4 to 5-bit DACs to provide high energy efficiency. Among all the array structures, we can see URA and CCA, they can provide the higher energy efficiency. Finally, here we plot the energy efficiency versus different bits of the Q of the DACs. So Q ranges from 1 to 10. And also for different values of the SNR, so SNR ranging from minus 20 to 20. So as we saw that at low SNR values, only 1 bit is sufficient to provide high energy efficiency because of the low sum rates. But if we increase the higher, if we have the higher SNR values, then maybe we require 4 to 5 bit of DACs to provide high energy efficiencies. Also, compared to all the array structures, we can see that CCA and URA, they can provide high energy efficiencies along with the higher sum rates as well. So in conclusion, in this paper, we propose the eigen decomposition based hybrid precoder design to analyze the performance of different array structures. We also designed the hybrid precoder using the case when we are using only the few bit DACs. The quantization noise is modeled using the additive quantization noise model. And the sum rate degradation is summarized here. So we can see that for 1-bit DACs, we are considering CCA only because CCA provides the highest sum rate. So for 1-bit DACs at very low SNR, close to 0 dB, we can see there is less degradation, approximately 20%. But at high SNR, by using only 1-bit DAC, we have a degradation of 60%. So this degradation is compared to the case when we are choosing the full resolution components. But if we use the 4-bit DACs, we can see that at low SNR, we have approximately 0% degradation. However, at high SNR, there is slightly 10% degradation. So we can consider 3 to 5-bit DACs for the use of the hybrid precoder instead of using the infinite bit DACs. And only 3 to 5 bits, they are sufficient to provide high energy efficiency and the higher sum rates compared to the fully digital precoding and the infinite bit DACs hybrid precoder. Also, among all the array structures, CCA and URA, they can give higher sum rate and energy efficiency compared to ULA and UCA. Thank you very much.